You're watching Neural Made Simple, where AI becomes clear one step at a time. Today, we are building a working house price predictor in Python. We will create a small dataset, separate training and testing examples, train a linear regression model, measure its errors, and estimate the price of one new house. The final project runs from beginning to end, and you can copy every file included with this lesson. This project is designed to teach the workflow, not to value real property. The dataset is synthetic, meaning we generated ourselves with realistic-looking relationships and random noise. A production valuation system would need verified local sales, richer location information, careful legal review, and ongoing monitoring. Here, the learning goal is to understand the code clearly and run it successfully. Start in an empty project folder. Create a Python virtual environment so the dependencies stay separate from other projects. Activate it, then install NumPy, pandas, and scikit-learn from the requirements file. Scikit-learn's official installation guide recommends an isolated environment because it reduces package conflicts. Once installation finishes, the same folder will hold our generator, dataset, training script, and results. The project begins with 4 simple files. Requirements.txt lists the packages. Generate sample data.py creates the synthetic house records. Houseprices.csv stores those records. TrainHousePriceModel.py loads the data and trains the predictor. After we run the model, it will also create predictionResults.csv so we can compare actual and predicted values. Open the data generator. We use NumPy's default random generator with a fixed seed of 42. A fixed seed means the random-looking values are reproducible, so you and I get the same data set and the same final metrics. We create 240 houses with floor area, bedrooms, age, distance from the city center, and a target price. The synthetic price starts with a base amount. More floor area and bedrooms increase it. Older houses and greater distance reduce it. We then add random noise, so the relationship is not perfectly clean. This gives linear regression a meaningful pattern to discover while keeping the example understandable. Finally, pandas writes all 240 rows to house prices.csv. Run the generator and open the CSV file. Each row represents one house, and each column has one consistent meaning. Before training any real project, you would inspect missing values, impossible numbers, duplicates, distributions, and possible data leakage. Our generated file is deliberately clean, but checking the data first is a habit worth building from your very first model. Now open the training script. We load the CSV with pandas. The 4 input columns become capital X: area, bedrooms, age, and distance. The price column becomes lowercase y, the target we want to predict. Keeping features separate from the target makes the learning task explicit. The model receives house details as input and learns to estimate the corresponding price. Next, train test split reserves 20% of the rows for testing. Random state 42 makes that split reproducible. We get 192 training rows and 48 testing rows. The model may learn from the training set, but it must not see the test answers during fitting. Those unseen rows provide a more honest check of how the learned relationship transfers. The code returns 4 objects: training features, training prices, and testing prices. Test size 0.2 creates the 80-20 split. We keep random state 42, so the same rows enter each group every time the lesson runs. Reproducibility makes debugging and comparison much easier while we learn. We create a linear regression model. It is a strong teaching choice because the code is short and the learned relationship is easy to explain. The model looks for coefficients that combine our 4 features into price estimates while minimizing squared prediction errors on the training data. More complex algorithms exist, but a simple baseline should come first when it fits the structure of the problem. The fit method is the training step. We pass xtrain and ytrain. During this call, the algorithm calculates the relationship between the input columns and the known training prices. When fit returns, the model contains learned coefficients and an intercept. It is now ready to apply the same relationship to house details it did not use during training. We call predict with xtest. The model produces one estimated price for each of the 48 unseen houses. Notice that we provide only the features. The real test prices remain separate in ytest. This separation lets us compare the predictions with reality after the model has committed to its answers, just like the closed-book test from the previous lesson. Our first metric is mean absolute error. It calculates the average absolute distance between the predicted and actual prices. On this generated dataset, the verified result is about $12,336. That means a typical prediction misses the known test price by roughly that amount. Lower is better, and the unit is easy to understand because it matches the target currency. The model's test, R-squared, is 0.982. In this controlled synthetic example, the linear model explains most of the variation in the test prices. That high score is expected because we created the data from a mostly linear relationship. It should not be treated as evidence that the same model would achieve this performance on messy real property markets. The script creates a results table containing the test features, actual price, and rounded predicted price. Saving this table makes evaluation concrete. You can sort by the largest errors, inspect unusual examples, and look for groups where the model struggles. A single summary metric is useful, but row-level comparisons often reveal the mistakes that matter most. Now we create a one-row pandas data frame for a new house, 1,850 square feet, 3 bedrooms, 8 years old, and 6.5 kilometers from the center. The column names and order match the training features. Consistency matters. A production pipeline should enforce the same preparation rules whenever new data reaches the model. Passing that row to model.predict produces a verified estimate of about $363,083. The number is not a professional appraisal. It is the output of our synthetic learning exercise. But the workflow is real. Collect examples, define features and target, split the data, fit a model, evaluate unseen predictions, and apply the trained model to one new example. Before using a model outside a lesson, ask what the dataset leaves out. Real prices can depend on neighborhood boundaries, renovation quality, land size, schools, interest rates, market timing, and many local factors. Errors may also affect groups differently. Good machine learning includes data documentation, baseline comparisons, validation, monitoring, and human judgment, not only a successful call to fit. You now have a complete beginner regression project. Generate the data, train the model, read the error metrics, inspect the results file, and change the new house features to test your understanding. The code and sample data are included with this video. In the next lesson, we will explain neural networks using a pizza shop, then connect that analogy to how weights and corrections work. Subscribe to Neural Made Simple and keep building one clear project at a time.